we use about 15 to 20 minutes to try to do 2 questions. So you are expected to practice at home, okay? So you are very familiar with the problem solving of those 2 questions, okay? Only focus on 2 questions each time. Yeah. All right. I just changed some numbers, okay? I do not change the question type significantly. Yeah. Basically, I changed a few numbers. Yeah. So your practice, you know, the method of the formula, you should try to memorize the formulas you used. Yeah. Because you cannot watch anything when you solve those problems. You have to use your memory to solve those problems. Yeah. Today is the first time. If some of you, if you're not ready for today, don't worry. So if you do not do well, because after today, you have so many sessions you can recover, right? Nothing to lose. Yeah. So you don't have any negative thing. Yeah. Each chance you won't get anything negative. Okay? You just try the best you can. All right. So that's one thing. Another thing regarding the points I give you back, I like to give you a little more information. Yeah, because think about this. Some students, if they already get a full credit for one particular question, then it looks like other people, theoretically, everyone can recover all the points for the midterm, right? Based on our current plan, everyone can get all the points recovered if you pay enough effort. Yeah, theoretically. Here I say theoretically. Okay, but here I thought about this. This way looks not quite fair for students who get all the points the first time, right? Yeah. So I like to do, you know, I try to make a fair way. I try to want to do this whole thing as fair as possible, you know. Yeah. What I mean is, for those students, if you did correctly the first time, I give you 1 bonus point. Bonus point, yeah? Because the first time you can do it correct. So you deserve only 1 bonus point, right? Okay? Yeah. 4 points total, but you get 1 more. So 4 plus 1 for 1 question. Okay? Yeah. Yeah. In this way, I try to make it fair to those students who did it correctly the first time. Yeah. Because I should not penalize those students. Okay?
Based on the tests that you have graded, how many people have gotten like the question completely correct?
I do not know. I just estimate. Here I only guess. You know, at least 2 students. Yeah, yeah. But other students possible. They're probably not completely. Yeah, but miss just 1 or 2. Yeah, yeah. Oh, I also need to do bookkeeping, because I need to write down for each student what questions you missed. You know, I need to do that bookkeeping. Yeah, because later when I give you 50% points back, I need to use the original points you get. Yeah, that bookkeeping. Yeah. Oh, another thing regarding the bonus point. If you only lost 1 point in 1 question, I also give you 1 bonus point. Okay, 1 point. 1 point, that means a very small minor error. Just the final answer incorrect. Everything correct. Okay, all the formulas step by step all correct, but last step not correct. That one I also give 1 bonus point. Okay. In that way, 3 plus 1, you get a 4. You do not need to do a recovery session, right? Yeah. Because if you lose 1 point, you're already full credit. Yeah. So that's the bonus point rule. Okay. Yeah. 3 or 4, you get 1 bonus point. Yeah. Other than that, then you do the recovery. Yeah. As much as you can. Yeah. Yeah. All right. So that's about the midterm. Yeah. Then I move to the final, because we need to start do our preparation right now for the final. Okay? Yeah. First, let me give you the annoying. Yeah. Oh, did you, you see? Oh, my side. Oh, okay. My side. All right. Yeah. Yeah. So here, final exam. Yeah. So we try to fix the problem we found in the midterm. Yeah. First, based on your feedback, it looks like too many questions, right, in 2 hours. Right? Yeah, I agree. I agree, too many questions. Even if we practice a lot, too many. So I want to reduce 2 questions. So in the final 2 hours, you get 8 questions, not 10 questions. Reduce 2. Okay, so each one 15 minutes on average. All right, so that's the first. Yeah. Still part A, part B. Okay, so final. Still, yeah, let me use the space here. Still, part A, part B. Part A, the quiz type, old quiz type, you know, concept questions, multiple choice, you know, those things. 1 week, still 1 week, okay? I post a little earlier, you know, give you 1 full week to do it. All right. Part B, that 2 hour in-class time, you know, yeah. Part A, because when I reduce the question number, I also need to adjust points for each question, right? Yeah. So here, you know, based on that, we need to do an adjustment. All right. Part A, this time, we get 9 questions, not 10. 9 times 4, each one still 4. So part A is 9 times 4, you get 36 points. Okay? Yeah. So then part B, because now 8 questions, you have 64 points, 8 by 8. How about that? Each question 8 points. 8 times 8, you get 64 points. Okay? Yeah. Total 100. Yeah. Yeah. Then, for the part B, here I also, you know, my plan. So what kind of questions I will give you. Yeah. Here, I can give you some information. So part B, in those 8 questions, in part B, okay, all right. First, the topic power series solutions, that topic, we have 2 questions, okay? Power series. And when we do our homework assignment, we will practice targeting on these questions. How about that? Okay? When we do homework number 2, number 3, I tell you, this question is targeted to final number 1, number 2, part B, number 3, and so on. Okay? So when you work on it, you can intentionally you do more practice. Okay? All right. So power series type, we have 2 questions. Okay? 2. Yeah. Because total 8. Yeah. So we cannot give too many. Yeah. So based on the top importance of the topic. Topic 2, that's the Laplace transform. We are learning right now that topic. This topic, 3 questions. This we know, the most important technique for this class. Yeah, so I give 1 more question, 3. Okay. Yeah. Topic 3, we haven't learned. In module 5, we will learn Fourier transforms. Okay. Fourier transform. Also important. Oh, I cannot write. Fourier, move. Too close to the boundary. Yeah, anyway, transform. 2 questions. Okay? 2 questions. The last one, only one, the remaining. Yeah. We need to go back to the last topic. Yeah. Yeah. We spend not much time, but we need to touch a little bit. Last topic. Linear algebra. Yeah. Related to linear algebra, using linear algebra to solve. Yeah. So we just do one more question. Okay? Last one is linear algebra. One more question. Okay? Yeah. Total 8. Yeah. Question? Yeah, system. Right. Yeah, system. System ODE, but we need to learn a little more. Okay? Yeah, we expand our knowledge a little more. Yeah, we already have some very basic, yeah, but we try to learn a few more advanced techniques. Okay? Yeah, here using linear algebra. Okay, using some, knowledge in linear algebra. Yeah. All right. Then, because here I only give you the topics, 4 topics, 8 questions, 4 topics. Then, in these, if we look at the computation and word problems, yeah, we also need to split. For direct computation questions, 5 of 8 solve ODE directly. Okay, yeah. And word problems, 3. Okay? Yeah. Word problem 3. Yeah. Yeah. That means because we have 4 topics, one of the 4 we cannot give word problem. Yeah. One of the 4 we cannot give word problem. So 3 of the 4, each one has 1 word problem. Okay? Yeah. Probably the first one, you do not have the word problem. First, power series. Then Laplace transform, you have 1 word problem. Fourier transform, you have 1 word problem. And the linear algebra, you have 1 word problem. Okay? Yeah. So that's my plan. Yeah. When we do homework assignment number 2 and number 3, number 3, we finished number 2. Number 3 and number 4, yeah. So I mark those questions fitting these 8 questions clearly. Okay? Yeah. Make you aware of them. When you work, you need to practice more than other questions. Okay? Yeah. These questions you need to practice more. Yeah. All right. That's my plan. So any question? Yeah. Any feedback? Yeah.
I guess, I don't know. I don't know. I still don't think I could finish 8 problems, but I think that's more reasonable to get done in 2 hours.
Yeah. Well, if you look at 8 questions, 2 hours, right now, definitely, it's hard, right? But think about, you practice after 2 assignments, homework number 2, number 3, do you still feel that hard? Right? 2 assignments, the same questions you go through, and you intentionally practice a few times while you feel still that hard, right? Yeah, think about that.
For the first test,
yeah. Anyway, right? Yeah. Yeah. The second time we try to do better than the first time, because first time we learned that experience. Okay. Yeah. All right. So that's for the remaining semester. So we still have chance, so we can get good results, right? Yeah, we still have chance to get good results. Yeah. Okay? Yeah. All right. Yeah. Yeah. Still use too much time. Yeah. Let's continue that Laplace transform today, and the next time I need to do another session, another class. Yeah. To next time I give you some more application questions. Yeah. Today we already have several application questions. Yeah. All right. Yeah. Yeah. So. First, this time because when we get this point now, we will consider the typical engineering problems. Here we will try to prepare ourselves for real-world application problems. All right, then for the real-world situations, then two special questions, very important, to help us model the real-world problems. In this topic, we work on those two special functions. The first one is the Heaviside function. Heaviside function, another name, unit step function. Because Heaviside, you do not know what is Heaviside function. But if you use another name, you can guess its meaning. Unit step function. These two words, it's a unit, the number, value, unit, that's one. Okay? Step. Step. Constant in a line segment, constant step function. All right. Definition. Definition so simple. You may see trivial. Why this function is important? Definition. U function. Because name unit step. So we take that u. U of t minus a parameter. You can change. It's a constant. It's a constant, but you have freedom to change or adjust that constant a. T variable. When little t less than parameter a, it's 0. Completely all 0. If t greater than a, look at the graph. Greater than a, all 1. All right? That's the unit step function. Why this function important? Because many real-world application questions, our ODE, right-hand side function, can be modeled by this function, right-hand side, not left-hand side. Right-hand side, the R function, little r function, the right-hand side of the equation. This is a important modeling function. We will see a few questions later. All right. So this is the original unit step function, but we can control because many times we need to use a parameter to adjust. Our function, because some action occurs at this point, a point, not necessarily at a 0 point, right? Sometimes some special action occurs at a time a, not time 0. So we need this version, shift. Unit step function shift a to the right. Basically the same. So we also need to consider that general case. Question: why we need to study the Heaviside function or unit step function? Answer: for solving ODEs with complicated right sides. Equality, right side of considerable engineering interest. Many real-world engineering problems, we need to use this function to describe right-hand side functions. Later you will see a few examples. Yeah. All right. Such as, yeah, here you have a few examples, such as single wave, single wave. Yeah. Wave, you have, many bump, up and down. Yeah. Single, only one, okay? One bump, yeah, single wave. Yeah. All right. Discontinuous driving force. The driving force not continuous, discontinuous. Yeah. Yeah. If that happens, we need to use this function to model the discontinuity. Discontinuity, yeah, very convenient. This function you can model discontinuity. The easiest way to model discontinuity. Yeah, yeah. But in our real world problems, it happens the driving force is discontinuous. Yeah. That could happen. Okay. Yeah. Periodic inputs. Yeah. Also. Yeah. All right. So for these special cases, we need to use the special function. Yeah. All right. Next, let's look at the Laplace transform. Yeah. Now we need to do the calculation. Yeah. By the definition, it's pretty simple. Yeah. This function is so easy, so simple. Yeah. The Laplace transform let us do the integral, the definition of Laplace transform on this simple function. Yeah. But here, yeah, I copy this formula from the textbook, but there is a typo. Yeah, there is a small error. So here, I need to let you know, yeah, when you read the textbook. Yeah. Look the lower limit here. It should be a, not 0. Yeah, a is not 0. Yeah. Because you can see after the, yeah, because this function, if you look at the graph, before a, it's 0. Okay? Before a, yeah. Let me show you. Did I show the graph? Yeah. Yeah. So I just draw the graph here. Okay, this is a. Okay. Before a, this function is 0. So your integral from 0 to a, gone. Okay. So the starting point is at a, not at 0. Okay. Yeah. Yeah. So then you do integration by parts. Then lower limit t equals a, the same, right? Otherwise, lower limit should be 0. Okay? But here, because that part, 0 removed, so the lower limit is a, yeah. Yeah. Not a 0. Yeah. All right, so then we have this formula. Then you see, yeah, the result. This is the formula. Yeah. So we derived. Yeah. Later, we just use this formula directly. Yeah. Yeah. All right. In this part, there are many formulas. Yeah. So don't worry. We just find somewhere, in the book, in the notes. Yeah. So then, we put aside, get it ready. So but you need to select the correct one. Yeah. In my examples, I will, explain how to select the right formulas. Yeah. Yeah. You need to get experience to select the right formulas. All right. Yeah. So then, now we need to consider, because the Heaviside function, usually we do not use it alone. Usually we use it together with another function. Yeah. Think about driving force. Driving force, you should have a special driving force function, right? Yeah. So f of 0 for all negative t, then we consider the product, a general function, product with the unit step function with the t variable a unit shift to the right. Yeah. So we consider that special case. So it's a f shifted, translated to the right by amount A. Yeah. So this form is frequently used. Yeah. This special form is frequently used to model the right side function of the ODE. Yeah. This form. Okay. Yeah. And not just one, multiple. Yeah. We have several such terms adding together, yeah, sometimes, yeah, several. Yeah. Because if you want to model discontinuity, yeah, think about discontinuity. So you need to use the building block. We treat this formulation, this is the building block to define a discontinuous driving force, yeah, something like that. Okay, all right. Here, use the graph to explain the meaning. Yeah, because if you look at that, what's the graph of this one? Yeah, you want to understand. Yeah. So here, let's use these three sine function to explain the meaning of this form. Yeah, the special form. All right. A, this is the original sine function, 5 times sine t. Yeah, here you can see that's the standard shape of the sine function, but you scale 5 times. All right. Then, if you use the original function f of t, multiply u of t minus 2, u of t, you cut off. Okay? Yeah, because before 2, all 0, all vanishing. Okay? All 0. After 2, you preserve the original function values after 2. But before 2, all set 0. That's the meaning of original function times t, u of t minus 2. All right. But in our real world problems, usually we do not do it in this way. Usually, we consider the case like this. Yeah. So we shift original function 2 units to the right, 2 units to the right of the t-axis. Yeah. Then we cut off. Okay? Yeah. After we shift 2 units to the right, then we draw a vertical line to set the left-hand side of that vertical line to 0 and preserve everything of its right-hand side. That's the meaning. Okay? That's the meaning of that special form. Shift, cutting off. Yeah. All right. Yeah. After we understand the geometric meaning, yeah, then we're ready to do the computation. Yeah. So because we know what we are doing. Yeah. All right. Then another useful theorem called a second shifting theorem. We have the first shifting theorem. Okay? Yeah. So I will copy the first shifting theorem. We do comparisons. Here, the second shifting theorem. What's that? First, we consider this function. Yeah, the function we just, try to understand. Yeah. This form, we take Laplace transform on it. Yeah. So this theorem tells us if we do Laplace transform on that special form, what is the result formula? All right. Here, 2 result formula, but 2 result formula essentially the same. Second one, just the inverse Laplace transform version of the first one. Yeah. So we treat them as the same. Content the same, but in different forms, so we can use one of the 2 in a special situation. Yeah. All right. So Laplace transform on it. Here, the right-hand side, you can see we only need to multiply a special factor, e function, e to the minus as function, multiply to the Laplace transform of f, original f without shift. Okay, original f without shift. So simple. Yeah. So when you see that. Similarly, if we, because it's a two-directional formulas. Yeah. So when you, sometimes you may want to start from left to right. Sometimes you go the opposite way, from right to left. Given right-hand side function, you want to get a left-hand side function. So you want to take the second formula. Yeah. Inverse Laplace transform of the right-hand side function. Assume it is known, you calculate the left-hand side function. Yeah. Yeah. All right. Yeah, so I wish the proof is simple. Yeah. One-line formula we can see by the definition. Yeah. All right. Here, let me recall the first shifting theorem. Yeah. Yeah. And we do comparison. Yeah. What's the difference between these two shifting theorems? Yeah. The first one, I copied the two formulas. Okay. The Laplace transform of, you multiply e function e to the at parameter a times little f function. Its Laplace transform is capital F. Yeah, capital F, Laplace transform of the original f function, capital F of s minus a. Shift inside the s variable. Yeah, that's the first shifting theorem. Yeah, okay. Then another one, just inverse Laplace version. Yeah. So sometimes we want to go opposite version. So we use the second formula. Yeah. All right. So these two formulas, when we solve different questions, yeah, we just select. So we copy, appropriate formulas. Yeah. Put aside. We just plug in. Yeah. All right. Next, let me show you quickly the proof. Yeah. Yeah. By the definition of the Laplace transform. Yeah. So let's calculate. Yeah. All right. Here, if special e function multiply Laplace transform of little f, yeah, by the definition, then we can do that. Yeah. Here, then you can change the dummy variable. Here, tau is the dummy variable of that integral, right? Can you change the dummy variable with a different variable, right? Yeah. All right. So after you change here, we change to t. Yeah. Yeah. T, you have a shift here, and the lower integral limit. You need to change to a. Yeah. You need to change to a. Yeah. Yeah. So here, yeah, actually, it's easy to see. Yeah. You just let t equals this tau plus a. Okay. So when tau equals 0, t equals a. That is your lower limit. Yeah. So every place. Yeah. So when you have tau, you write it as t minus a. So you replace f of tau replaced by f of t minus a, and so on. Yeah, it's so easy. Yeah, yeah. Just do this, simple operation. Yeah. Then this form you can use. Yeah. Look at that. Yeah. This form you can use the, this special form. Yeah. So Laplace transform of this function. Yeah. Okay? Yeah. That's the proof. Yeah. Yeah. All right. Yeah. Yeah. Do you want, can you see why this function equals that? Yeah, because that cut off, right? Yeah. Cut off. Yeah. Here you can see. Yeah. All right. Let me say a few words explain, because I'm afraid a few students may not get it. Yeah. So let me explain a little more. All right. Look at, so before we multiply that u function, okay? Yeah. So before this line, okay? Before multiply that function, the lower limit lower integral limit is a. It is a. Okay? All right. So then, because we know the special property of that Heaviside function, unit step function, that starting point at a, we can extend it to 0. Yeah. But the extended part, how do you fix that extended part? By this unit step function. That function is used to fill that gap. Okay? Yeah. So you didn't add anything there. Yeah. You just use a special view to understand that formula. Yeah. You use a special view on it. Okay? Yeah. All right. So that's the reason we take this formula. Yeah. All right. So that's a brief proof of this formula. So later, you just apply the formula with confidence. Okay? Yeah. Yeah. It must be correct. Yeah. All right. Next. D.2, examples with Heaviside function. So let's solve a few examples in this topic. Yeah. Example, given Laplace transform of a function. Yeah. 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 All right. So find, and we want to find the inverse transform. Yeah. So we practice using those basic formulas. Yeah. All right. Yeah, it looks pretty complicated, right? Look at the capital F of S. 3 fractions, sum of 3 fractions. Yeah. Although pretty complicated, but if you look at the structure, denominator s squared plus pi squared, yeah, sounds familiar, right? So we use this kind of format many times. Yeah, looks so familiar. Yeah. And also this one. Yeah, all right. Then, let me copy the right basic formulas. Yeah. Remember last time, table 6.1, I copied many formulas. Yeah, last time. Yeah. Here we still use those formulas. Yeah. All right. First, I copy this formula. Laplace transform of sine omega t is this fraction, omega over s squared plus omega squared. Okay. Can you compare? Yeah. With the first term, second term. Here you can see the first term, second term, you can apply this formula, this basic formula. Okay? Omega constant. So you don't worry about that omega constant. So you can do division, to change it easily. Yeah. Omega constant. Okay? Yeah. Second formula, basic formula, we want to, formula number 2 in that table, 6.1. That's the Laplace transform of t equals 1 over s squared. Yeah. Look at this third term, denominator s plus 2 squared. So let's look at the s squared first. Yeah. S squared. So we can use this formula. For plus 2, remember, we have 2 shifting theorems, right? First shifting theorem, second shifting theorem. Those 2 theorems would help us fix that plus 2 problem. Okay? Yeah. So we have everything. Yeah. Yeah. Here, this one, yeah. Yeah. All right. So this formula, yeah, I copied Laplace transform of this special form. Yeah. This one you can see because look at the numerator of these 3 terms. Numerator, you have an e function. So this formula we can use some e function multiply some f function. Yeah. So this formula, inverse transform, we can write the left-hand side form, yeah, to get a numerator e function property. Okay, all right, yeah. So we addressed everything in the right-hand side formula, everything. Now we can do the calculation. Yeah. All right. And another one, yeah, here, yeah, because shift, yeah, this formula, yeah, this is the shift formula, okay? This one is used to take care of this s plus 2. Yeah, s plus 2. We need to calculate. So this formula tells us how to work on the s plus 2 part. Yeah. All right, so now we have everything. Yeah. So we just put those pieces together, we find a solution. Yeah. So let's do step by step. Yeah. The first step, let's work on the first term, but let's ignore that numerator e function first. Yeah. So we apply this formula 8 inverse of this right-hand side fraction, omega equals pi equals sine of pi t. Can we just divide that numerator pi both sides to get this function? Okay? Yeah. Step by step. Each step we only, do small progress. Small progress. We can understand. We don't jump too fast. Okay? Yeah. So now you have that. Okay? All right. Yeah. So let's work. Yeah. All right. So then the next one, this time we add numerator e to the minus s. So that means we should apply this function, right? Okay? E to the minus s, that means a, little a is 1. Okay? Little a is 1. F of s. That f, this is f of s, right? Yeah, we just found it. Sorry, this is capital F of s. This is a little f of s, right? Capital F of s. Little f of s. Yeah. Fitting into that formula. So our understanding. Okay? Capital F of s, little f of s. All right. Yeah. Then let's apply this formula. Little f of s, but this time you need to replace t by t minus a. A equals 1, so t minus 1. All right? Then little u function, u of t minus 1. Yeah. Yeah. So you get that inverse Laplace transform. Okay? Yeah, be patient. Yeah. Yeah. So apply the formulas carefully. Yeah. Each step only do one small progress. Yeah. All right. Similarly, yeah, because the second one, similar to the first one, the only difference is the 2. Yeah. Only difference is little a, the shift, the result shift little a, we change from 1 to 2. We change from this 1 to 2. So we get a second term. Yeah. Much easier, the second term. Yeah. Then the last term. Last term structure completely different. So we cannot use the above computation. We have to start a new computation. Yeah. All right. The new computation, we start here, right? Yeah, because this formula has the root of that structure, the root. All right. So inverse 1 over s squared equals t from formula number 2. That's our first step. After that, let's do shift. Let's do s minus a shift. Okay? Because plus a, look at that, plus a, what should be, plus 2, what should be that a? Positive 2 or negative 2? S plus 2 should match s minus a, right? So a is negative 2. A negative 2, so you use e to the negative 2 t, right? Yeah. Yeah. All right. So e to the negative 2t times, yeah, because the original function, yeah, that t. Yeah. That, yeah, because e to the negative 2t times original f. Original f is t. Original little f is t. Okay? Yeah. So we just use this formula carefully. Okay? Yeah. So when you write down, carefully, so we get, all right. After that, not done yet, we need to address the numerator e to the negative 3s. Yeah. That is, so here, e to the negative as, a equals 3, right? E to the negative 3s times f of s, okay? This is f of s, all right? So we use that formula, all right? So now, after we add that e to the negative 3s, then this function, based on the formula here, that function, because that's the little f, right? That's the little f. Little f function, you replace t by t minus a. A is 3, so t minus 3. Okay. Replace t by t minus 3. All right. After that, you multiply. Oh, sorry. This should be t, not u. Yeah. After that, yeah, this typo. Yeah. Yeah. This is t minus 3. Yeah. U times t minus 3. Yeah. So there, you have all three terms. Last step, you just put them together. Okay? Last step, little f, the inverse, yeah, because sum of all three functions. Sum of all three functions. Yeah. Final solution. Yeah, that's the final solution. Okay? Yeah. So when you do calculation like this, be careful. Yeah. When you apply, because shift this way, that way, those formulas. So you need to get a lot of experience. When you practice, try to get a lot of experience. Okay? Yeah. All right. Yeah. But in the final, you can use, open book, open notes, right? Yeah. It's not in our recovery session. You cannot use. Okay? Because I want to make sure you can do it independently. Yeah. You can. You have the skills to do basic things. Those are basic things. Yeah. All right. Yeah, but the final, you don't worry about that. So you can use all the materials. Yeah. All right. Yeah. Then to draw the graph, draw graph like that. Yeah. So here, the first part between 1 and 2, that function. You use the first term. Yeah. But between 2 and 3, why this piece is missing? Because cancellation. Because the first term, second term, 1 above the horizontal axis. Yeah, here, let me draw this way. Okay, 1 above, another below. Plus, minus cancel out. Okay? So it's gone. Yeah. So in this interval, this is below the axis. The first term below the axis. Okay? Second term above the axis, positive. Yeah. But adding together, cancellation. So it's gone. Okay? Then after 3, you use the third term. Yeah. Because the cancellation cancel all the way down to the end. Okay? Yeah. Because everywhere cancellation. All right? Not just here. Yeah. Remaining interval, all cancellation. Yeah. All gone. Yeah. Yeah. So that's why you do not see after 2. If you do not look at the third term, that's 0. That's all 0. Okay. All canceled out. Yeah. All right. Yeah. So we are at a break time. Okay. All right. So that's